Hey everyone, thank you for joining. Um, Originally, my colleague was meant to present this, but she could not make it today, so I'll be presenting at her stead. Um, oops. Yeah. Cool. So there's a QR code for the link to the repo. And also there's a custom JupyterHub instance where we'll have like the data that we'll be looking at and some notebooks. But feel free to go directly. So if this is visible, this is the repo, my GitHub username and Pytorch serving. But you can also directly go to the JupyterHub instance, which might be shorter. It's just hub2.np.training. And it contains the repo and yeah. Also, inside the repo, you can find the slides that we're going over under assets and slides. So if you want to revisit them during the session or offline. So let me get started. So the agenda for, sorry, I hope everyone got this, but yes. So the agenda for today, I wanted to kind of briefly talk about machine learning at Walmart search, review some deep learning concepts, just make sure we're all kind of on the same page. Talk about how do you take a model that was trained and how do you optimize it for production, and deploy the model with TorchServe from Facebook, and yeah, briefly talk about some lessons learned. After each kind of section, there is kind of like a hands-on. So please feel free to ask questions in between or during those sessions. Yeah, so I'm a machine learning engineer at Walmart Search, and my colleague Ravi is also here today. Yeah, so how in a search system, where can machine learning be used? It's not just something like a user enters a query. There are things like spell check, correcting like mistakes that a user might have made, like type ahead recommending things so that a user wouldn't have to type the full context, related searches, creating item embeddings, creating query embeddings, parsing the query intent. So there can be many layers where machine learning is used. For today's session, let's mainly focus on the query understanding. So let's say we have a query like Nike men's shoes. A good query understanding system should probably understand that there's a brand intent of Nike, there's a gender intent of men, there's a product type intent of like kind of athletic shoes versus like maybe casual or dress shoes. And let's assume like in the catalog, all these attributes are parsed kind of properly. So once you understand the query intent of Nike men's shoes, can you match it to the item side? So there can be several models just involved in this piece, but today let's just focus on, given a query, can I parse the product type correctly? So briefly, like what was the production infrastructure at Walmart? So last year we had several production models written in TensorFlow, and since we were like a Java shop, we had them. We were serving these models as services using the Java native interface. Just like everyone, we saw the benefit of large transformer models like Bert, so we kind of wanted to start seeing how we can use that to enrich like the different layers in the search stack. We wanted to build something that supported PyTorch and kind of Onyx as a general framework for supporting any future models. And since this is serving the model in production, we wanted an SLA of less than like the peak SLA of 40 milliseconds, but ideally under like 15 would be really great. Yeah, so let me briefly introduce the data that we'll be looking at today. UC Berkeley and Amazon has this nice kind of e-commerce data where it has like product data, catalog images, 3D models, pretty rich data. But for today's session, since we are only going to build like a product type classifier, we're going to just look at the product metadata. So if you look at the product metadata, we have things like brand, item ID, item name, and product type. So what our model is going to do is, like, given the item name, here's kind of item title, given like an item title or given a query, can we extract the appropriate product type for it? And in the end, we'll deploy this model on ToadServe. It has a post endpoint where we can basically just give it the query, and we'll get the top predictions. This workshop, we won't really deal with training because training can take a long time. So I've already trained the model and made it available inside that JupyterHub environment. So we'll mainly look at, trying to see like reviewing how to do inference with this model, review the inference time for this model, look into some techniques for optimizing the model, packaging it with ToadServe. So that's basically the high-level overview. Again, if you want to follow along, there's the JupyterHub instance. The bit.ly link just takes you to the Git repo. Yeah, and inside the Git repo, there are the slides also that that are being covered. So yeah, let me get started with the first. Let me just briefly show some notebooks we have here. So inside this environment, so we're not going to deal with like the processing or training here, but Amazon and UC Berkeley made this really nice data set available. So this is this kind of what the data frame looks like. But since in our case, since we're dealing with like item title, that's really the main attribute that we'll be dealing with. And we have about 147K records. So it's a pretty decent data set. And just to maybe not deal with like pandas, we just create like a Hugging Face data set with these fields here. And then just did a train test split. So yeah, so the model's already trained. Let's just maybe go directly to kind of how would you build a classifier for this model? So let me go here. So, before Bert, before transformer models, if you want to build like a simple text classification model, you might do something where you might tokenize the input, you might feed it to a word embedding layer, you might feed it into your LSTM or RNN layer. Maybe you might have several of those layers stacked, and then you might have like a classification, either like a sigmoid or a softmax, depending on whether it can be product type could be whether a single item can have multiple product types. Yeah, this is this was a model similar to this is what we had in production for a very long time. You can fine tune your word embeddings with your own corpus, so you don't just need to use the general word to vec. And if you add like bidirectionality, you can kind of get pretty good accuracy for this. There's some cons with this model, and I think Bert as a transformer model can have solved these things. One thing is like tokenization is always a problem with something like word to vec, which is just a simple word tokenization algorithm. Like if there's like any new tokens that are coming in the user's query, if you use exact match, you might miss them. So something like a subword tokenizer might be able to solve some of those issues. Contextualized embeddings, like depending on how long the query is, you might have some scenarios where a simple word to vec approach might not be capturing the right context. You'll see an example of this from our trained model. Word to vec is a pretty scalable approach for training embeddings, but it's not like you're not really training the embeddings on your downstream task properly. So Bert kind of with its pre-training kind of does a that's a better way of training that problem. And Bert in general is a general language model. So it can learn much better contextualized word representations than word2vec. So the other thing is, when we talk about Bert, like there are many different variants of Bert, like different sizes of Bert. Bert base has 12 layers, but there are other smaller variants of Bert that have different numbers of encoders. And as you can see by the the Stanford sentiment dataset accuracy, depending on the number of encoders and the architecture, you can go all the way from 83% accuracy to close to 90% accuracy. Obviously, the larger the model it is, the higher the inference time will be. So this is an example of the model that, this is an example of the results for the model that we had before and the Bert model that we build in our company. So for a query like betting for twin extra large mattress, kind of the BioSTM model, the top prediction is mattress, probably because like the mattress is the last token. But the actual intent of this query is kind of like the betting. So with the Bert model that was trained, bet sheets is the top extracted product type. So in general, like on our holdout validation data set, the F1 score improved from 0.75 to 0.91. So this is definitely a great model, and we definitely wanted to push it to production, especially looking at the metrics. So let's maybe look at, like if you're new to like the Hugging Face dataset, APIs, let's kind of see how to use the pre-trained model to kind of do inference, or fine-tuned model in this case rather. So let me go to this notebook. So I'll be going over, training is a bit difficult to do in the settings. So we'll just be looking at this inference review notebook. Let me just duplicate in case, feel free to follow along or read the rendered run. Let me just clear this screen on this. I hope this is big enough to see. Hugging Face has done a lot for the open source ecosystem. So we're importing the transformers library from there. And since this is a Pytorch model, we're importing Torch and some other dependencies on it. I've already fine-tuned this model on this data set. So I'm just going to load the checkpoint using the transformers helper libraries, helper classes. So here is a distill Bert model. So for given a text, it's a 768 dimension embedding, and we have like 30 product types from this data set. So things like accessory, handbag. So let's see for some queries here, like how do you do inference? So we have a query here. We have our tokenizer. We tell it to, there's only like 5 valid tokens, but we tell it to pad it to the maximum length. And then we have like an attention mask for like where the tokens were actually used. And then once we get this one pair of input IDs and attention mask, we feed it into the model that we saw before. And we get the model outputs. And in this case, the model was trained as a softmax. So we just apply softmax and get the top end results here. So here's the probability, here's the items, and let's just map it to the labels that we saw before. So what was the query here? Yeah, cheap professional men's shoes, right? So, the top class is 99% on this. So, yeah, the Bert model is very large to visualize, but this is a distilled Bert base model, so there should be like 6 encoder layers. But yeah, it's maybe a little bit difficult to see, so I'll just skip this for now. What else? Yeah, and I just have some helper code to see like the accuracy and results, but let me just go for the rendered output. So on this data set, this model is getting about 0.95% or 95% accuracy. Yeah, so the one thing to take a look at, how long does it take to run inference? So this model on a CPU takes about 124 milliseconds. On a GPU, it takes about 25 milliseconds. So this is just something to keep in mind when serving in production. So let's look at the second notebook where we compare the timing. Oh, sorry, before I go to the next notebook, are there any questions about the material so far? Yes?
So I know so, and I know this is more of an engineering-based talk, but is there a way to kind of summarize the Bert, like the way the Bert model works here in terms of, are you kind of just taking some intermediate embedding from Bert and then training the softmax on top of that and just basically doing a multi-class classification?
Yeah, I mean, so with the Hugging Face, sorry, I didn't go over the training code here, but like in this case, I just used the Hugging Face transformers library. So, so it does, this helper class order model for sequence classification. It just takes Bert, it takes the embedding, and then it adds, I think by default, like one additional layer, and then trains it as the classification piece. You can use like regular Pytorch or Pytorch Lightning to add multiple fully connected layers or more complex heads that's needed.
Cool, thanks.
Yep. So go to this other notebook just to kind of give an intuition for how long some of these models take. Let me just again duplicate this in case, and please feel free to follow along or just look at the rendered output. So let me. In this notebook, we're going to look at different variants of Bert. So there's the Bert large model. Oh, it looks like I didn't download the checkpoint. Yeah, so there's the Bert large model. We're going to look at the Bert base model. So Bert base has 6 encoder heads. And then we're going to look at the distilled Bert model. We'll cover distillation later in the presentation. And we also saw in the previous notebook the timing for distilled Bert. So yes, for the same query, let's just see. It's running the inference time now. Definitely these models, it will be challenging to run in a CPU environment in production. So let's see if we can see some of these results coming up here. Let me also just bring let's see. Maybe this will take a little bit of time. So let's just look at the rendered output here. So when I did this run a while back, so for the for the Bert large model, for a single query, it takes 734 milliseconds. Yeah, that's close to a second. That's pretty large, especially for an online use case. On a GPU, it's about like 278 milliseconds. So not that much improvement, relatively speaking. So Bert base, which has half the encoders, so it's 217 milliseconds. On a GPU, we're getting about 43 milliseconds. So that's maybe on the higher end, like that we have in our production use case, but this is possibly a candidate. The distilled Bert model, on a CPU, we're getting 112 milliseconds. And on a GPU, we're getting about 26 milliseconds. So this is kind of ideal in our in our production use case. But I hope you can see, like, depending on the model, the number of encoder layers, you can go all the way from like 26 milliseconds to 278 milliseconds. And this is assuming like, obviously there's a much larger expense cost when you're serving on a CPU versus a GPU. So that's also something to keep in mind, not just the time. Yeah, so I think these were the two notebooks I wanted to go over for the first part. Are there any questions before I switch? Yes?
So I'm curious on like what environment is this running on? So because the other day there's another speaker mentioned that if you run it locally, you found this a great improvement, but then you run it on distributed environment, then you find out it actually not changing that much.
Yeah, so these timing informations are like running on GCP, like on a N1 Hyman 16, so like the 16-core machine. And the GPU is a T4 instance. I think like in the cloud environment, you're kind of limited to what NVIDIA kind of allows for the GPUs. But I think like the T4 is a pretty decent GPU for like runtime inference. But all these numbers are like for kind of like a small batch size of one. Like definitely like in a batch inference use case, you can get much better throughput and much better runtime for the GPU. So those numbers, when you average it, might give a better picture. Yeah, hope that answered that question. Cool. Let me go to the next section if there are not any other questions. Sorry. So I hope you saw, like, depending on the BERT model you use, it can definitely take some effort. It can definitely affect your latency and time to serve for the users. And definitely in an online setting, this can be very important. So what are some techniques that we can use to improve that latency, if any? Definitely we saw distillation drastically reduce the model inference time. So let's briefly cover that also. But let's first talk about the first technique, which is pretty commonly used, called quantization. So when we train our model, like we trained it on 32-bit precision floats. But do we really need such a high level of precision, especially for all the layers? Maybe for some of the layers, we could probably convey the same amount of information with like 16 bits or with ints, 8-bit ints. So if we were able to reduce the level of precision, we could reduce the memory, and also like accelerators like GPUs still are faster for int-based computations. Definitely a CPU is much faster for int-based operations. So in the image here, we have like a histogram where you have like the full float distribution. But if you could maybe map it to the scope of an int, you definitely see like in the bottom chart, like we have a loss of information and precision, but it kind of might capture the shape of your data enough, especially for some of the layers, it might be sufficient. So if you can find that mapping, it might work for your model. And the whole idea here is that because int-based computations is faster, if you can have some layers of your model using this, not only do you reduce the memory consumption needed, you can also increase the computation speed. And Pytorch supports 3 different types of quantization. The first one is you quantize the weights of your network. So you have your model saved, you quantize the weights, you save it. Then during runtime, as the input goes through the model. When you do the multiplication with the weights, you quantize the activations, and then you do the multiplication with the weights, and then you feed it over to the next layer. So you keep doing this operation of like mapping the activations to ints and then multiplying it with the weights. But yeah, so you keep having this operation of mapping from floats to ints, but depending on the layers that you do it, it might not be a big drop in accuracy. One benefit of using this approach is, you can do it on your model that's already trained. You don't need to do any operation for, like having a calibration data or whatnot. So this is a very easy operation to do. And you can also choose to do it only for some layers. The two other techniques that here's an example in Pytorch, which is called torch.quantization.quantizeDynamic. And then in this thing here, you see we are passing just the linear layers of the model. And we're telling it for that specific layer, we want to use int-based quantization. The other two techniques are kind of similar. One is static-based quantization. Here you're quantizing both the weights and the activation, but in order to do that, you need some calibration data. So while the model, in the previous step, like we had these activations that was being quantized on the fly, but here, because we're giving some calibration data, it will find like a much better mapping. And because there's no like converting back to floats to ints back to floats, a performance on this model should be faster. There's a slight variant to this called like static quantization or quantization aware training. The idea is like if you're going to quantize your model, why not consider your quantization error as part of while your model is being trained? So not only will your model be trained to reduce the accuracy, improve the accuracy or training loss, you can tell your model, I want you to also optimize the quantization error loss. This leads to the best results. Let's look at how the results look in practice. So, three different type of models. So, Bert, ResNet, and MobileNet for image classification. The first column, the 32-bit accuracy. For Bert, let's just focus on that. So we have about 90%. If you change it to int-based accuracy for like the linear layers, you get about 89%. So that's still good. But if you look at the inference performance, we have about close to 2x speed up. I think that's really great for like such a very minimal drop in accuracy. But if you look at other things like for like ResNet 50, let me see. Yeah, so for ResNet 50, like for some of these convolution models, you can't really do like this dynamic quantization. You need to do like static quantization or quantization aware training. So with those techniques, you get also like a 2x, and in the case of MobileNet, you're getting like a close to a 6x performance, going all the way from close to 100 milliseconds to 17 milliseconds. The MobileNet numbers is like numbers on a phone. So on like more edge devices, you might see the benefit of quantization more. So the other technique that you can use to optimize your model inference time is distillation. The idea is like maybe when you train your model, you might have a large teacher model, or you might have a large model that kind of tries to explore the whole space. But once this large model has explored the space, you might try to distill that information to maybe a smaller model. So large models like Bert, especially with the large number of encoders, it has a large learning capacity. But maybe like a BiLSTM, it just cannot capture maybe all that information in your information space. So let's look at the results of this model in practice. So, so let's consider a Bert large model. So on the Stanford sentiment data set, it has about like a 95% accuracy. And you have a student model, a BioSTM model. So the BioSTM model by itself has about like an 86% accuracy. But if you distill that model with the information that was learned from Bert large, you get about a 90% accuracy. So a BioSTM model is very cheap to kind of serve and run. And by the fact that you were able to increase it like by 4% by just distillation is a great improvement. And yeah, so those were like the two main things, like quantization, distillation. The other thing is like a small thing to just keep in mind is like one of the reasons why Pytorch became very popular is the fact that by default it was in eager execution mode. While TensorFlow kind of made it a little bit difficult and it was always in graph mode and it was a little bit hard to debug. But there's a cost for kind of this ease of use. This eager execution mode is not ideal for production, although it allows you to get immediate feedback. So in order to make it ideal for production, you need to convert it to script mode. And one of the things that happens in script mode is you're creating an optimized execution graph. And when you convert your model to script mode, you can also just serve it in a pure C++ runtime. You kind of decouple the Python, the Python bindings or use case for that. And technically, it's also representing the model in like TorchScript, which is like a PyTorch's intermediate representation of this model. Yeah. So this is just something to keep in mind is that this is a step that you might need to take. But luckily, PyTorch makes it easy to go to script mode. Yeah, just some small details, like maybe in the future this might be fixed, but right now there's like 2 different types of ways to convert it to script mode. But the basic idea is like you're passing it some input data and TorchScript looks at how the model gets activated and tries to create like an optimized execution graph. One type, tracing, is more flexible, but scripting is maybe a little bit more performant, but there might be some limitations. So one limitation is, so if in your operation you're doing like if-else operations, like in this forward step, if you're doing a different step, like changing the weights or something based on the input, this is something like the script mode might not be able to support. So let's see what is the improvement that we get. So here, we're taking the same model, same PyTorch model, and you're doing this torch scripting process that we just talked about. So we're going from 1.3 seconds all the way to 768 milliseconds by just doing that tracing operation that we talked about. Definitely, you see a large improvement on this CPU, and GPU by raw numbers is a little bit smaller, but you're still seeing improvements here. So we explored three techniques: quantization, distillation, and this execution of tracing. So let's kind of explore these things in a lab. So this is covered in lab. Let me just shut down all the kernels. So this would be in optimizing the model. And all these models, they have some, all these notebooks have intermediate files, but the intermediate files are also included in this environment. So if you want to just follow along with a specific notebook, you should be able to do that. So let me just duplicate this notebook. Yeah, maybe before I run this notebook, are there any questions on the slides so far? Cool. Yeah, let me just run this. So we are taking this model that was trained, fine-tuned on our use case. Yeah, it's just some tokenizing. I just create like a subset so we can just evaluate the results of the model. So we covered 3 things, right? Dynamic quantization, static quantization, and quantization of where training. If you want to do like static quantization, we need to give it some calibration data, so which might be a little bit difficult. So for now, I'm just going to use dynamic quantization. So as we saw, like we can choose to give which layers we want to quantize and the level of quantization. So like if we look at the regular Distilbert model, we see like there's several linear layers here. Right? In the transformer, there's several linear layers here. So what we are saying is for those type of layers, we want to convert them to 8-bit ins. So after doing that operation, we see like the layer type has changed. We also see that the size of the model has changed. So it was before 267 MB, and now it's 138. Since not all the model layers are quantized, so that's why you don't really see like a 4x kind of decreasing, going from 32-bit to 8-bit. Yeah, so let's see if the quantization time has run. So yeah, what do I want to mention here? So for the original model, we had 306 milliseconds. Just that single quantization, we reduced a bit here to 246 milliseconds. And this is already a distilled Bert model, so we're doing this optimization on top of that. There are some limitations in Pytorch about like, at least when I ran this notebook a while back, it didn't support like quantization for some of the for some of the layers for like in a GPU environment. I think this issue is fixed now, but yeah. So a quantized linear layer is only available for the CPU backend. But I think this issue is fixed now. So when I did this results, I computed this results in the past. So for this Distilbert model, the accuracy, as you see, is like there's not really much drop, especially for this data set. But we went from 116 milliseconds on a CPU to 83 milliseconds with quantization. And again, this model, a Distilbert model on a GPU, can run inference in 17 milliseconds. So they've already met our use case at work by distilling and running on the GPU, but we can still see improvements on the CPU. Yeah, so TorchScript, luckily Hugging Face makes it a little bit easy. So you can, when you load the wrapper class, you can say like TorchScript equals true, and there's like some decoupling that needs to happen inside the model, but luckily luckily Hugging Face makes it easy. Yeah, let me see if I have numbers for that. Yeah, I think this is let me see if I have one more notebook here. Yeah, I think this is the final thing where I outputted here. So as we mentioned, for torch scripting, there's scripting or tracing, but at least in this data set and in this environment, with our regular 32-bit floating point precision, we save like 6 milliseconds by just keeping the same level of precision. But after like quantizing and tracing, we can reduce it all the way to 90 milliseconds. So like all these small things like can add up a little bit, but maybe it's not as much visible in this data set. Yes, so sorry, are there any questions before I go to the next section on, oh yes.
So apart from just running through Pytorch and quantizing new positive, why not check a different runtime mechanics?
Yeah.
Sorry. Instead of just quantizing like different weights and just still using PyTorch?
Yeah.
Why not go to like a more inference optimized runtime like Onyx?
Yeah, that's a great question. So I didn't have the notebooks for Onyx, but like at work, that's the environment that we use.
Okay.
We started with the Pytorch the Torch script kind of runtime, but then we moved directly to Onyx. I think Onyx, especially I think Hugging Face has a new library, Optuna or something, like where it makes this process much simpler, and it also does things like layer fusion, which we didn't really talk about here. But yeah, that's a great point. Yes.
Thank you.
Yes.
To what extent do these techniques apply to like the BART model, or is it more Hugging Face dependent?
Well, I mean, the techniques that we talked about are not even specific to PyTorch. Like you can even do it with TensorFlow. Like they are.
I mean BART versus BERT. Oh, okay.
Oh, I don't know the details about BART, but like things like quantization, we saw it being used like it, you know, like for like CNNs even. So quantization is a global technique that can be used everywhere.
What I meant was, to what extent how hard is it to do if you're not using Hugging Face's
Oh,
techniques, which you've
yeah.
been showing?
So as you, so in a regular PyTorch model, like maybe in the slides, like quantization is one of the most easiest thing to do. Like you're just using regular torch, and there's no Hugging Face wrapper or anything. So definitely that's easiest to do. I think like as another person mentioned, like I think the Onyx runtime does a lot more things like operator fusions and all those things. So that also can just be used with a regular torch model. You don't need to use like the Hugging Face wrapper or whatnot, although they have a new wrapper that makes it very easy. Cool. So let's see. Yeah, so I'm going to go on the last section here where, so, whichever technique you used or combination of techniques, we now have like a PyTorch binary that we want to serve. So how do you want to go about serving it? So the first option that you could do, especially if you're in the Python ecosystem, is use a regular web server like Flask or Fast API or variants of that. Or you can use one of those model-specific frameworks like TorchServe from Facebook or NVIDIA Triton. Or if this was a regular TensorFlow model, you could use TensorFlow serving. So, what are some benefits of kind of using TorchServe or / a model serving option, a model server option? So one is, like Flask, Fast API, they're very nice and simple to get started with, but there are some different considerations you need to think about when you are serving models. So you might have a scenario where in the same web server, same service, you want to serve multiple models, and maybe one model you want to serve it with CPU, another model you want to serve it on GPUs. And maybe for the CPU, like 2 CPU models, one of them you want to allocate more workers, and one of them you just want to allocate 1 worker. So something like TorchServe or NVIDIA Triton allows or supports multi-model serving. Another thing to think about is like, especially in production, you might have a use case where you might have a model that's serving prod, and then you have a case where you want to test a new variant of a model. So things like model versioning and handling those requests, I think the model serving frameworks are built a little bit to think about that. The other benefit is like server-side batching. So if you have a scenario where you're getting high number of requests, if by default, like fast API of Flask, it's dealing with a single request. And even if they're served on a GPU, they're always going to be sending a single request to the GPU. But these model serving frameworks, what you can do is you can say like, hey, if I'm getting a certain number of requests and they all come within like 2 milliseconds or something, I want you to automatically take all those requests, batch them together to the GPU. So this makes better usage of the GPU and can decrease your latency. And also, these model frameworks kind of support like the notion of like pre-processing and post-processing the input, which is, it's not just feeding the input. As you saw, when we passed the model, we needed to tokenize it, then we needed to parse the mapping. So frameworks like these have better conceptualized that idea compared to just a regular web server. So how do you use ToadServe, which is from Facebook? So there's the first step you need to do is create like a MAR file, which right now is just basically like a zip file. So Torch has a utility called the Torch Model Archiver. You give it like a model name, model version. You give it the path to your PyTorch file. You tell it where you want to export it, and you tell it what other packages you want to package as part of your MAR file. So that might include like your tokenizer config. It might include like any other config files that you want your model handler to read when it does inference. And then the final thing is you need to give a reference to a PyTorch file that will handle the request once it comes to your handler. This is a bit maybe small, but this is if I'm writing a handler completely from scratch. So in a handler, the main method is called handle. So in the handle method, when you have an input, there's a pre-process step, an inference step, and a post-process step. If your use case is very similar to what some of the handlers that Facebook has already provided, you can use the existing method. But if not, you can also override those steps. So these steps, like pre-process and post-process, there's already a default implementation provided by the inbuilt ToadServe handler. But you can also override it for your use case. And these are some of the default handlers that are already provided for inside PyTorch. So if you have an image classifier, you just need to add like maybe 2-3 lines of code because you can use the existing handlers that are provided by Facebook. And then you have your MAR file. How do you actually serve it? So in ToadServe, which is the actual web server, you give it a config file that basically says which models you want to load, which IP addresses you want it to listen, the location of your models, and this is the batch size that we talked about. So we want to ideally create batch sizes of 20 with a maximum delay of 2 milliseconds. So if you're getting like hundreds of requests and they all come like per millisecond, ToadServe will automatically batch them with batch sizes 20, feed it to your GPU, debatch it, and send it to your handlers. It's all kind of all kind of abstract in a nice manner. So you have started your web service. ToadServe has 2 endpoints or 3 endpoints that they expose. One is like a management API. You can show which models are there, what versions they're being served, what is the number of handlers that are being served there. And then when you make a post request to 8080 in this case, and the model name, similar to TensorFlow serving, with the post request, it goes to your handler method and returns what you have defined in your handle method, either the post-process method. So let's look at the small notebook for actually serving this piece. So this will be the last notebook. So let's see. So this is just the help stuff for Torch Model Archiver. We kind of saw these things in the slides. So in our case, since this is like version 1 of our model, I just called it version 1, model name as PT classifier. The location of the model, so this is where, when I called like the transformers library.save, this is where the model is there. I also have the traced model if I wanted to serve that. Yeah, and this is just the handler.py code. Let me just go here. So this is if I'm defining everything from scratch, right? If you're using like existing handlers, you don't need to do it. But like in your case at work or whatnot, if you want to build something standard, so maybe one thing you want to do is like when your request is coming in, you want to log it in a certain way. When a request is being post-processed, you want to maybe send some metrics to a different service. So you can kind of build something like a generic handler for your use case. So onboarding future models are easy. But in general, your request comes to your handle method. You have like the context. You can send the data to your pre-process, inference, and post-process steps. So like let's look at, so in the use case that we have here, like the pre-process step, I read all the requests. It might be coming in the body. I compute the, I tokenize it, gets the input ID's attention mask, and then feed it to, and just return this piece here. At my inference step, I'm getting this batch that's provided, and I just feed it to the model. And I can do the mapping of the IDs to the labels in the post-process step or in the inference step itself. So you do have some flexibility there. And again, this is if you're implementing the handler completely from scratch. There are some built-in handlers where you don't need to implement all these. So I packaged a model. There's a MAR file. Right now, it's just basically a zip file. So you can actually use like zip to unzip it and see it. This is the handler that we talked about. Let's see. So I copied the MAR file to like my model store folder, which is just empty. You can just put the files there. And then in toteserve, this is the command you can use to run it. Let's see. So once toteserve start, it provides these logs, so the metrics logs, and these logs which you can also push to Prometheus or whatever monitoring system that you have. Again, if you look at the logs, we see the model has started. These are the endpoints by default that are provided, but you can override them as needed. If I hit this admin endpoint, I see that I have one model loaded. If I hit that specific model, I see details like how many workers are provided. By default, it will use all the CPU workers that are available, and on a GPU, it'll create one worker per GPU. Yeah, so batch size is just one. And this is how you can make a simple request to the model. Herbal tea, here in this case, it's under grocery. The example of what we saw before. Yeah, so, and one small final slide that I had, sorry, this image is a bit small, but we already, like, so this is with all those metrics that are emitted from toteserve, you can build a Grafana dashboard. The model that we talked about, the PT classification model, after like distillation and actually also serving on Onyx, we are getting like under 7 milliseconds. So definitely distillation, quantization, Onyx, these things can definitely be used to make serving these large transformer models reasonable in production. We are serving on GPUs, so that's also why we're getting like under 10 milliseconds. Yeah, and this is the last slide I had. Did anyone have any questions on notebooks or materials that was covered so far? Yes.
Have you experimented with faster transformer and seen improvements with that?
Yeah, so there was a colleague that experimented with fast transformers, but I think there was like some issue that we had when packaging it with TorchServe when we first explored it,
Right.
but we haven't explored it since like 6 months ago. So yeah, I'm not sure.
So if you use the faster transformer route, Triton has the ability to support faster transformer directly natively in it.
Okay.
So you don't need to go through Pytorch or Torch.
Okay. Yeah. One reason why we weren't necessarily impressed with like Triton per se is like we wanted to add some flexibility like for pre-processing and post-processing step, like in defining it in Python itself. And when we looked at Triton back then, it seemed definitely there was a gap, but we haven't explored it since then.
So in the last year, Triton's added something called a Python backend where you can use pure Python code to run pre-processing or the model itself directly, even post-process.
Okay, awesome. Yeah, didn't know about that. Thank you. That's something to look at. Yeah. Yes.
You looked into like caching some of the embeddings, I assume for like very common queries and stuff like that.
Yeah. So one thing I didn't mention here is like it's very expensive and maybe not worth like serving every single request live from the model. So and if you think like in an e-commerce setting where there's like head traffic and tail traffic, probably for head traffic you can have a cache. I mean, especially there's no like context here. Like if you give a query, like it's not like the PT changes, so you can definitely cache it for like days even. So definitely you don't need to hit the model for every request. Yeah, so that's a great point. Yes. Yes.
Hey, thank you for the talk. This covers a lot of stuff that I've been working on poorly. And I mean, your talk covered it well. My work is being done poorly. There are a lot of libraries out there that purport to be like kind of optimized, like optimizers for like that. Like I know Olive does it now. Onyx Runtime, I think, does distillation and does quantization for you. Have you seen like what? I have a couple different questions here, but the first part is: are there any particular standouts in auto applying, a library that really does a good job of applying distillation and quantization in particular? And what's the most promising stuff in the field in your opinion? Because we've got the Pytorch auto optimizer, we've got the Olive optimizer, we've got the Onyx runtime optimizer. So it's kind of hard to navigate all these things when you're new to the field.
Yeah, I think like recently, like Hugging Face has a new library that makes it easier to use like the Onyx runtime. I think it's like just 2 lines, like for dynamic quantization, it's just like 2 lines of code. So like from the ease of use, I think that definitely like the Hugging Face library makes it easy. I think like quantization is a technique that's very easy to use. Whether using regular like the PyTorch bindings or like some other wrappers around it. I think like distillation, especially like going back to dynamic quantization, since you don't need to provide like any calibration data or whatnot, it's just calling those APIs. But static quantization or quantization aware training, like we tried exploring quantization aware training, but it can just be a little bit difficult to kind of get the model architecture correct. But I think now there are like some libraries or helpers that make it easy. But I think for us, like we have kind of stuck with like Onyx. Just find it kind of abstracts like some of those fusions and things a little bit easy. But definitely for our case, we needed to serve on a GPU to kind of meet our SLA. So. Cool. Are there any other questions? Cool. Yeah, I mean, so here's a repo. The slides that were covered are inside here, and the notebooks are here. Feel free to peruse them, and yeah, feel free to reach out in the future or whatnot for any questions or whatnot. Yeah, thanks everyone.